All right, so let's talk about this machine learning one. This is an important issue. When you have data and you're going to subject it to a machine learning model, you can't just feed it into a machine learning model. In fact, you have to do a lot of pre-processing of the data, and you even have to make judgment calls and change things. So once you load the packages you need, so here's where you download this data. This is a housing data set, and I think it came from the government. It's something about the prices of houses in California in the 90s. Broken up into little zones, which seem to be counties or something smaller than counties. And the data has all these things: longitude, latitude, the age of the house, the rooms and bedrooms, the population of the zone, the number of households, the income, and the house value. And our goal is going to be to try to predict the house value from these other parameters. And also ocean proximity. So you can use head to see the first few rows of any database, and here you can see all of them are numbers. You can do averages and mathematical operations on them, except the last one is alphabetical. So that's going to be one challenge to overcome. And so now you can do categories and counts of the last one to see what there are, and you see there are really only 5 possible values: inland, near ocean, near bay, island, and less than 1 ocean. Not sure what that means. Something like far from the ocean, I guess, or within some region of the ocean. Anyway, those are the 5 categories. All right. And so you can do statistics of all these numeric fields. You can get mean, standard deviation, and all that jazz to get an idea how they scale. And then you can start doing things that are going to help you clean up the data. The histogram is probably the first start. So if you do a histogram, now you know in normal statistics, if you have an ordinary thing you measure, you get a Gaussian distribution. But of course, this is not that kind of phenomenon. In California, most of the houses are either up in San Francisco or they're in LA. So there's 2 peaks of longitude and latitude where most of the houses are. So you don't get that distribution. And here's the median age, which has a strange structure, suggesting probably that houses were built in some waves, like after World War II, they built a bunch of houses and so on. So the ages are even. Notice this, though, a huge spike at the end. That's the kind of thing that probably is going to get us in trouble. That would suggest that the data just has a maximum of 50 years, and it puts all houses over than 50 years, it calls them 50. There probably isn't a huge spike like that of houses that are exactly 50 years old. This is probably an artifact in the data, not really representing the population. And that's the fundamental problem here. Your data is not perfect. Nobody's data is perfect, and so you have to try to find the flaws and clean it up. Now, so these are the distribution of the fundamental parameters. By the way, notice the same thing about house value. It seems to have a maximum, and they lumped everything above that in this one spike here, and you probably don't want to train on that because that's, again, not really representative of the real underlying phenomenon you're measuring. That's some kind of defect of the measurements made here. So here's another issue. If you make training and test sets, remember you choose some random items, take 80% of them to train on, then you hold back 20% to test your model later, then there's a problem with biased sampling. So consider this. If you have something that is sex-linked, for example, we just did it, voting. Women voted much more for Kamala, men voted much more for Trump. So if you tried to predict how something would go just on sex, the sex of the people would matter. And if you did random sampling, there's like 51% women, and so that's the most likely thing, but you have a pretty chance of getting like 53 or 54% women in your sample just by random chance. And if you do that, your sample is not representative of the population. So instead of choosing random elements, what you do is you do what's called stratified sampling. And so here, we're going to do that for income, because as you would imagine, and we'll see later, income is a huge predictor of house price, obviously. If the people are poor, they have cheaper houses. If the people are rich, they have more expensive houses. So we group income into 5 categories, make 5 bins, and then instead of just randomly sampling, we find out what the population has, what percentage in each of these 5 categories, and then sample that many percent of each of these categories. So the sample is representative of the population, instead of being completely random. And so you can split the data and see the results. And here's the example. The training set has 35% category 3 and 31% category 2. And now my test set has exactly the same percentage. Since I didn't choose them completely randomly, I chose them randomly within each group to get the right number. This is called stratified sampling. And when I first came across this I used to be a regular scientist studying physical parameters of proteins and stuff, and you'd never modify your data like this. This would be putting in a bias. But when you have data like this that has biases, then you have to try and compensate for it. And it means that maybe you're going to be wrong. You're kind of taking a risk manipulating data in this fashion, but it's what you have to do. In cases like this, where you have data and the data is expensive and you can't easily get more data, and you have to figure out how to use the data you have and compensate for its biases. And this is very much true of polls. And as we saw again last night, the polls were again spectacularly wrong. The last 3 elections, all the polls have been wrong. They're wrong again. So this is an unsolved problem. People take all these, they ask thousands of people who they're going to vote for, and then they try to sort them into categories and adjust the numbers. And obviously, they haven't figured out how to do it for the last 3 elections, because they have to have models that say, this group has this many people, and we'll multiply this by a factor. In this group, I've oversampled, so I'll lower it. And you base that on some previous elections, and the problem is in the modern elections, Donald Trump is not like any other politician. People are not voting for him in the usual way, so your models of how the different groups will lean are wrong, so you have failed to predict. And so anyway, now, and if you don't do the stratified sampling, then you get different, like this is 35 and this one's 34, this is 31 and that's 32 and so on. All right, so now you can visualize the data. This is often very important to find flaws in it. Here's the geographical layout of the data. Now this is extremely misleading, because as we saw before, almost all the houses are in the San Francisco Bay Area or in the Los Angeles area, and yet here it looks like they're almost even throughout the state, and that's because when a whole lot of dots pile up, they just pile up and turn blue, and you can't see that. So it would be better to use transparent dots, so you can now see that this is really dense and this is much less dense. And the next thing you can do is include the population and the price. You have over here is the house value in the color, and the population is, I think, in the size of the dots. So now you can see a lot more that these areas have not only the most population, they also have the most expensive houses, as you'd expect in the San Francisco area and in the LA area. But the correlations are where you really get to the meat of this. So correlations are where you're trying to predict housing value, and this will tell you which parameter is useful. And so here, this is house value against median income. And you can clearly see there's a real trend here. If the income goes up, the housing price goes up. There's a straight line passing through here that will catch most of the variation, and that's what correlation coefficients are. Correlation coefficients you calculate with simple statistics, and it's 1 if there's 100% predictability, and it's 0 if there's no predictability at all. And here you're going to get a correlation coefficient, and I think this one was 0.7. So that's very predictive. Median income is a very strong predictor of housing value. Now, if you look through here, most of these are nearly 0. After that, the only things that are significantly predictive are total rooms and latitude. The fact that this is negative doesn't matter. And so, let's see if I have total rooms. I do have total rooms. So here's total rooms against income, and well, it's messier than that, but I guess there's some tendency, especially down here, to have some increase in the value as you go up in total rooms. And here is median age, and boy, that correlation is not very impressive at all. So with this, you can see some things to do. If you blow up the main one here, income versus value, and take a good look at it, you're going to see a lot more things to notice. Here's the one I noticed before. There's a huge cluster of dots at 500,000, which is clearly not real. It's some kind of limit in the data. Anything above that, they round it down to this. So we're going to have to remove these points. You either have to remove them or you have to replace them at points where you expect them to be. If you leave those in, you're going to learn, your model is going to learn something that's not true. And notice there's more of it. Here's one at 450, here's one at 350. So apparently some of your data was rounded off. For all the ones that should be spread through this block are shoved in the middle, and that's not right. So you're going to have to remove those data points or adjust them in some way. And that's another disturbing human putting an input into this, massaging the data. But you have to do it if you want to get, and here's something I found more interesting. In the world of statistics, you like to have multiple independent measures of something, because then you can average them and average out the noise. But that only happens when you have independent measures. Now, if you have data here like rooms and population and bedrooms and distance from the bay, it's not clear that those are independent. You don't know how correlated they are. So it turns out, remember up here, to try to predict the housing price, we had correlation coefficients here, 1.7, 0.13, 0.10, and then a bunch of trash. It's not necessary that these parameters are the best parameters to predict things. In fact, you can combine them. You can get rooms per house, total rooms over total households, bedroom ratio, total bedrooms over total rooms. You can construct new parameters out of the ones you have, and they might be more predictive, and in fact, they are. Rooms per house goes up to 14% predictive total, and bedrooms ratio goes up to 25% predictive, far more predictive than any of these other parameters alone, so other than median income. So this is another thing to try, and you'll see this a lot in machine learning. You create new parameters by combining the existing ones, even though you might think they're not independent. The new parameter might be more useful than the individual parameters were alone. So that's a few things you do in pre-processing, and interesting concepts to know, and it helps. Like most of my machine learning training, my main message is machine learning is a whole lot less powerful and less scientific than people think it is. It's doing something that's only a little bit different than the old-fashioned curve fitting I did 50 years ago. It's not this momentous new thing that is going to make robots as smart as humans and replace us all. It is so far from that. It's just a little bit ahead of the old curve fitting. Anyway, let me stop this one.